grade later on in the final. So that's the reason you need it. Your name is here, and then you can sign here. I know some students probably have the last minute and just registered for this course, and your name is not showing up. I downloaded it about weeks ago. So there's no change, but if there's something change, you write it down on website. Okay, website. So the last thing I want to say, okay, everybody is so far, and you make it the speaker here a little bit and more effort with the louder, so better than the content from, okay, and this means your approval. Yeah. It's to be a work you said, I want to be related. That's not there. Yeah. So everything fine so far, yeah. I have not seen the slide down there.
I muted. I muted until I get the.
Okay. Good, thank you. Yeah, for everybody. Okay, it's time for start the first colloquium today. And you already know, and our speaker today is Dr. John Hiller. He is our department chair, right? Department chair. And this talk is supposed to give last semester, due to some kind of university, as everybody knows, sometimes when there's not concert, there's concert to this semester, and I put a number one talk in this semester. Okay, so and let me take my glass, otherwise I cannot see so clear. So Dr. Hiller, Professor Hiller, and got the MS and the PhD in theoretical physics, University of Maryland, very good university, and the postdoc in the Institute of Advanced Study in Princeton and Purdue University. Now, earlier is a physics faculty member in the University of Minnesota, and now is the professor and the chair in our department. And he will give a talk. The title is Gravity and Quantum Mechanics, and Newton, Schrödinger, and Einstein, Klein, Gordon, Soliton. So one thing I need to say about that. So last year, and the Nobel Prize given to the quantum physicists. So the quantum, entanglement. You guys know about that. So that's the reason I invited and so many professors, doctors, and we were a little bit focused in this semester about the quantum phenomena. Yeah. So you will have a lot of opportunities to and listen such kind of expert talking about quantum effect. Okay, good. Just to give a little bit more. Yeah, please.
Thank you.
Go ahead.
Thanks for fitting me in. It was an unfortunate situation last fall, of course. I'm not going to be talking about quantum entanglement at all, although there are people who, when they're worried about true quantum gravity, which I'm not going to be talking about, but when they do talk about quantum gravity, entanglement is part of the picture. People have been thinking about ways in which entanglement has something to say about the underlying structure of space-time from a quantum mechanical perspective. But that is pretty much the limit of what I know on the topic. Instead, what I want to be talking about today is the way in which to interpret a semi-classical view of gravity, in the sense that particles will be treated quantum mechanically and the gravity would be treated classically. So doing general relativity as far as the gravity side and quantum mechanics on the particle side. But I also look at things from the standpoint of a non-relativistic description, where it's then appropriate to talk about Schrodinger and Newtonian gravity rather than GR. So I'll talk about that as well. But let me start just by reminding people that the notion of a black hole dates way back to 1783, and independently Laplace in 1795. Mitchell is actually the first. You can go to this URL here to see some of the history that APS has listed for us. But basically the idea is that light cannot escape from radii that are less than this amount, is 2g m over c squared, where m is the source mass that we're trying to get away from, and g is Newton's gravitational constant. And that simply comes from the fact that anytime you do an escape speed calculation, you want to have at least enough energy to get out to infinity. And so you need this expression for the energy to be set to 0. And here I put already the speed at c, the speed of light. And so this directly tells you that r has to be bigger than this if you want to be able to get away. But the other way of looking at this is it says that any point particle is a black hole. Any particle that has no size is automatically inside its Schwarzschild radius. Quantum mechanics, though, says a particle doesn't have a definite location. So you can think quantum mechanically of a particle as being a source for gravity as being spread out in some way. So basically what we were doing was looking at what that meant from a relativistic standpoint. The non-relativistic calculation for spherical symmetry has been done since the 90s. So it's known, but we replicated some of those calculations just to be able to make some comparisons. But anyway, the idea is then to a semi-classical treatment where you couple classical gravity, either Einsteinian or Newtonian, to a quantum mechanical particle, where the quantum mechanical particle is described by either the Klein-Gordon equation, which is a relativistic equation, or Schrodinger equation for the non-relativistic case. One way to think about it is that this particle being spread out creates an energy density within the space-time. And that, of course, in parlance of gravity, is a source for curvature. And so you look for having that probability density be reinterpreted as a mass density, and that mass density then drives the creation of a gravitational field that contains the particle. So you have to have a self-consistent solution between gravity and quantum mechanics to represent that. Now, in working units where h bar is 1 and c is 1, which is typical for a particle physicist, but since I'm not a general relativist, I keep capital G out explicit. And for our universe, it has a rather interesting value in terms of particle physics type units, the GeV being an energy unit. Capital G goes like 10 to the minus 39 per GeV squared. It is really tiny, okay? And so the sorts of things that I'm talking about are a little hard to imagine actually being interpreted in a laboratory, because you're talking about gravity being extremely weak. Getting an echo here. Somebody got.
I need to.
You can mute. Okay. Thanks. No.
I muted.
There. No, there's one through that one.
Okay. I'm probably just leave it.
Because I want to see who is participating online in the.
You can just turn your computer sound.
Okay, I leave that.
You're off? Okay.
Yeah, I'm all
All right.
Yeah.
So for most of the discussion, I'm going to limit things to spherical symmetry. At the end, I'll come back and talk about a cylindrical symmetry. You look at the non-relativistic case, it's the Schrodinger equation with Newtonian gravity. For GR, then you look at gravity really in terms of curvature. So you got to represent that in terms of space-time metric. Talk about that a little bit. Introduce the Klein-Gordon equation, which is a relativistic equation that can be written in terms of a curved space-time. So we solve the relativistic extension of Schrodinger's work to curved space-time. General relativity equations would tell us about the metric itself that then feeds back into the Klein-Gordon equation. And to supplement that, we have the Tolman-Oppenheimer or Volkov equation or TOV equation for the pressure, where we make the assumption that this probability distribution acts like an ideal fluid. And so we basically have a nonlinear quantum mechanics problem if you think about the potential that appears within the Schrodinger equation or within the Klein-Gordon equation as being the result of a self-coupling. So that potential itself depends upon the wave function, but you find the wave function by solving the equation. So it's nonlinear. So let's set that up for the non-relativistic case. Here's the Schrodinger equation for a modified radial wave function where you pulled out this factor of R so that it reduces down to what looks like a one-dimensional equation in terms of the radial variable. Remember, we're working in terms of spherical symmetry here. And with h bar equals 1, so there's no h bar appearing inside this equation. The mass distribution is going to be the mass times the probability distribution from the solution to this equation. And so it is going to be proportional to the square of this wave function u, normalized in the usual way. Now, if we have that kind of a density distribution, the strength of the gravitational force comes automatically from Gauss's law. And it's just an integral over the density inside the range at which you're computing the force strength. And from that, we can calculate a potential, integrating in from infinity so that our potential is 0 to infinity, which is what we usually do as a choice for reference point. And we can rewrite that in terms of this wave function u. There are various manipulations you have to go through, changing limits and so on. But it boils down to this expression. So we go back to the Schrodinger equation. This potential right here depends upon knowing u. And you put that in to solve this equation. So you want to solve it iteratively by solving this equation for a guess for v, take that solution, recompute v, put this back in, and so on. Solve it iteratively. But it's clearly a nonlinear situation. And there's a whole literature on the nonlinear Schrodinger equation, which you could think of as branching off from this, where you can make all sorts of choices for the potential. It's not necessarily a gravitational situation. And so people look at those sorts of things. Now, it's convenient for doing numerical calculation to rescale things, to recognize what are the important scales that are present in the problem. And for the non-relativistic problem, as you might well imagine, there is some analog of the Bohr radius, which is called the gravitational Bohr radius. And we get that simply by looking at the comparison between a Coulomb interaction and a Newtonian interaction. In the Coulomb interaction, you'd have in the ordinary Bohr radius, 4 pi epsilon naught over e squared, as well as the m. But this 4 pi epsilon naught over e squared, well, that's just 1 over gm squared. Because the 1 over r potential for gravity is gmm over r. And for electrostatics, it's e squared over 4 pi epsilon naught r. So that correspondence tells you what the natural gravitational Bohr radius is. It's this 1/gm cubed. We don't have two different masses here, remember, we only have the one mass present in the problem. Natural energy scale, g squared times m to the fifth. Remember, g goes like 1/energy squared in my units of h bar and c being 1. So g squared goes like energy, 1/energy to the fourth, and m to the 5 goes like energy to the fifth. So this product has units of energy. And so we define some dimensionless quantities, epsilon, zeta, a u tilde, a v tilde, all with the corresponding unit pulled out from them, and then rewrite that system as this equation, which came from the Schrodinger equation, and this relationship that lets us calculate the potential as a function of that wave function. These things can be solved numerically. You just introduce a discrete grid where you know zeta values at some equally spaced points, and you represent this second derivative as a finite difference approximation, represent the integrals here with a trapezoidal rule, and then carry out the diagonalization to extract the energies from this representation. Yes?
How do you pick your starting point on stuff? Is it given your common convergence issues or with multiple costs?
We found that it converges pretty readily. So if you pick anything halfway reasonable, what we did was take a hydrogen atom wave function shape. So we have an exponential fall off and a simple polynomial. Put that in as a wave function, calculate what the potential looks like, put it back in, and solve it. And it converged quickly. Yeah. When I first sat down to do this sort of thing, I was worried that there would be serious convergence issues in that kind of iterative approach, but it turned out to be not a concern, surprisingly. So here are some results.
Sorry, can I
question
interrupt?
online?
Yeah, can I interrupt you?
Let me turn the volume up.
Yeah, can you hear me?
I have to turn the volume up.
Oh,
So, Roop, you want to try again?
yeah. Can you hear me?
You're better, yeah.
Blah, blah, blah. No. How come it's so low? Is it better now? Anyhow, in case you hear me, my question is the following. Isn't your problem similar to the ordinary, the non-relativistic version of your gravitational problem here? Isn't it very similar to the standard Coulomb problem for hydrogen, except that because the Coulomb potential in hydrogen is 1/r and gravitational potential is 1/r. So these are they're parallels. The difference being that in standard hydrogen, we assume, of course, a point Coulomb, while you do not assume a point gravitational potential. But the whole difference is you assume a broad source, while in the standard simple hydrogen problem, we assume a point source. So when it comes then to guessing wave function, could you then, at least for the long range part, use the hydrogen wave functions? In the short range part, probably have to do some modification. Would that give you, I mean, is this analogy or this parallel between the two problems? Did I say that right? Would you agree with that?
Yes,
Would that
yes.
enlighten the insight into this problem?
Yeah. That's why we used a hydrogenic wave function as an initial guess to get the iteration started in this non-relativistic case, because the lowest order approximation is that you have some sort of point source, and then look at how that gets fuzzed out as the iterations proceed.
Okay, thank you.
So the second column has the results for this non-relativistic calculation. And there are three. And we're getting more echoes again. The little n.
You're broadcasting the sound.
Mute already. Not for me. Somebody.
No, you're not muted. Now you are. Yeah. I just muted you. Okay. Okay, so this n index refers to the number of radial nodes in the solution. And remember, we're looking at spherically symmetric case, so there's no angular momentum part here. The non-relativistic eigenvalues are these. This is the dimensionless one, so you have to multiply them by g squared and m to the fifth to get a physical value. These other columns have to do with the relativistic calculation, which is associated with a second length scale, which is the Schwarzschild radius. I'll say more about that later. There's a PhD thesis, not aware of the details being published at all, but the thesis is available. And he has done a very high precision calculation for the non-relativistic case, and these numbers match up to the accuracy that we're doing the calculation. And you can see the relativistic effects as this zeta s getting larger and larger means more and more relativistic effects, and you can see the eigenvalues tending away from the non-relativistic value as you go up. Here are the probability amplitudes for these three cases. This is the lowest one. Of course, there's no node here. And these are more spread out than you would expect for a hydrogen atom. And the reason for that is that each one of these corresponds to a different potential. Because remember, you have to have a self-consistent solution where the wave function determines the potential. And in this next plot are the effective potentials associated with each of these cases. So for n equals 0, the potential is much deeper here because the particle is much more localized, much closer in to the center. And those that are more spread out are associated with effective potentials that are less deep and themselves more spread out. This does go to 0 eventually when you go way, way out. But the activity is in this general region if you look at those plots before. See, it's the same 140 here. So each one of those wave functions goes with a different effective potential because you're looking for a self-consistent solution between the two equations. But now what about a relativistic approach, which is what we really started out looking at, thinking about. And the idea here is that space-time gravity is represented in terms of curvature, and that is encapsulated in the metric, which is a 4x4 matrix of functions. And it could be, for example, that you have a structure that determines distances within your space-time, where these g values determine the coefficient. So in this case, there are no off-diagonal terms, and it's determining the invariant distance within the space-time scaled by different factors depending on which direction, which axis you're talking about. If these things are all constant, then you're dealing with a flat space-time. But if they have a functional dependence, and in particular the Schwarzschild metric here, which you can find in Carol's nice book about space-time and geometry, that the solution for general relativity outside of spherical mass distribution can be given by this metric specified by these functions, and the G00 and GRR depend upon the radial position. And so compared to a flat space-time, it would have no distortion at all. You have this distortion in the short shell metric where the source is down here, and you get curvature of paths as they pass by and so on. Again, I'm using C=1, so that's disappeared from any formulas you might have seen before, even at the first slide in the talk. Now, the Klein-Gordon equation in a curved space-time looks a little bit messy, but basically have contributions of the metric defining what you mean by the differentiations that are taking place. So this is just a general curvilinear coordinates setting up how the differentiations have to work in that case in order to have the proper space-time invariance in your equation. So this is the Klein-Gordon equation. And in a flat space-time, this becomes very simple. You just have a simple second derivative with respect to time. That is a big distinction with respect to the Schrodinger equation, that this is second order in time. But it's the only way to have a nicely invariant relativistic formulation. For a curved spherically symmetric space-time, you can write it all out in terms of spherical coordinates. Looks like this. And I've defined a G tilde to combine some of the factors. And if it's static, so that the metric doesn't depend upon time, and that's what we're interested in, it simplifies much further because things can come outside of these time derivatives here. And so it reduces down to this form where I've introduced L squared, your standard angular momentum operator. So we can set up this relativistic equation for doing the calculation. We do a separation of variables. So we can pull out the spherical harmonics that are the eigenfunctions of L squared. We can pull out a function of time and do this separation where we have a separation constant that we pick in such a way that it's a natural choice for energy. The time function is solving this separate equation for the time function, and it's quite straightforward. You just get the usual exponential. And so in this case, the probability density is stationary, which is what we want. So we have a static situation. And the radial equation that comes from this looks like this. So it's almost like the normal radial equation you would get. I see there's a typo here. This R to the L should not be there. It's already been put over to the other side. So that should be gone. The only difference is that you've got the presence of these metric functions showing up inside this term. If those all went away, then you would be back to the ordinary radial equation that you would frequently see. Now, did some work with this with a student, Rebecca Lin at Duluth. Sophia and I were just looking at solving the Klein-Gordon equation in curved space-time with chosen potential dependents showing up inside the metric. In other words, basically choosing the metric and not looking at the self-consistent solution where the metric is driven by the probability distribution from the Klein-Gordon equation. But we did have then some experience with solving this equation, at least numerically already. We want to also introduce a modified radial wave function in this case, because with the differential derivative terms there become are rather complicated and when you write them all out. But if you introduce an additional function h here, you can simplify that equation quite a bit. And it turns out that if you set h to be this combination, then you get a very simple equation replacing the original Klein-Gordon equation. In the Schrodinger equation context, h would be just equal to r. But in this case, where you have space-time curvature present, there are some additional factors. But with those included, we then get a relatively simple equation for this function. And we have a normalization condition that it should obey. And because we're integrating over a curved space-time, there's a metric factor there as well. But in any case, we can define a probability density. We've been writing things for general L here. In fact, the work with Rebecca, we looked at non-zero L. But here we're only interested in spherically symmetric distributions because we only want to solve the GR equations for a spherically symmetric source. So we're only interested in L equals 0 beyond this point. So we need to compute the metric. We have a mass density that we know once we solve the Klein-Gordon equation. And the way that feeds in is that the metric functions, when you have spherically symmetric distribution, look like this. You can find this in a book by Griffiths and Podolsky. And this function is just an integral of the density. This capital phi has to satisfy a first order differential equation, with P being the pressure. And so we needed an extra little bit in order to be able to determine the pressure. And so we made this assumption of the TOB equation. And so the pressure is driven by this also first order equation. We know what the boundary conditions need to be. The pressure should go to 0 at infinity, that the mass function should go to 0 at the origin, because this integral is becomes 0 once r goes to 0. And at large r, this phi function should take on the form you'd expect from the Schwarzschild solution. So these equations, we have an equation for the pressure, we've got an equation for this capital phi, we've got to compute mu by doing an integral. They all have to be solved simultaneously with the Klein-Gordon equation, which is where rho comes from. So again, we have to do a self-consistent solution of all these equations. And we do that not with them directly as written, but we again do some rescaling. It's always good to do this in order to stay within a good dynamic range, what you're dealing with, and so you understand what the natural scales are for the problem. The Schwarzschild radius is 2g times little m, and that introduces a second length in this problem. And that means we have a dimensionless ratio between the Schwarzschild radius and the gravitational Bohr radius. And that we call the zeta sub s. It's essentially a dimensionless Schwarzschild radius. And it's this combination of factors, g squared times n to the fourth. And I'll show on the next slide that this does determine how important relativistic effects are. We have these scales present. We can rescale all the different quantities that are available in the problem. And that gives us a rescaled system of equations. The first one being the remnant of the Klein-Gordon equation after all that processing that was done. And then the equations that come out of GR and TOV in order to calculate the metric. And this was work done with Dustin Taylor, who was a physics and mechanical engineering major here. And he just graduated last summer. So this system of equations needs to be solved simultaneously. And so again, question?
I was gonna ask if you could expand on the ideal pressures, ideal liquid fluid.
I mean, where do the TOV equations come from?
Yeah, what's the, help me understand. What's the pressure? It matters?
It's essentially an assumed equation of state for this ideal fluid. So it's incompressible and zero viscosity. And based on the equation of state for that fluid, and then there's a relationship between the pressure and the density.
Okay, thank you.
Yeah. So this is a system that needs to be solved by making some initial guess. And basically, if I remember correctly, what we guessed was a Schwarzschild metric outside some radius and then constant inside. Because we're never pressing things to where it's going to collapse into a black hole. Okay. The matter density never reaches the point where where we have collapse problems. That could certainly exist as some extreme relativistic solution of these equations, but we never went looking for trouble. Okay. From some perspectives, of course, that may be the interesting solution, depending on what kind of physics you're interested in. But that wasn't what we were interested in, so we did not push to that point. But let me comment on this limit of zeta s being going to zero being the analog of recovering the non-relativistic calculation. And one way to see that is to see what happens to a particle that lives in the Schwarzschild geometry. So it has some source with a mass, and it has non-relativistically, then it should have a potential that goes like 1 over r. And if you look at the metric for the Schwarzschild, look at the Schwarzschild metric and calculate the different pieces that go into our modified equation that comes from Klein-Gordon equation, it looks like this. And then if you expand that to first order in zeta s and collect the terms that depend upon zeta s, you find a standard Coulomb problem with terms proportional to zeta s as corrections to that. And so the limit of zeta s goes to 0 within this Schwarzschild geometry. You recover a standard non-relativistic Schrodinger equation. And so that shows that zeta s tells you the importance of relativistic corrections for the problem. And so that's why we looked at a range of zeta s values going from very small up to on the order of 1, on the order of unity.
Sorry,
So here
John, can I interrupt again?
Yeah.
Can you hear me?
Yes, I can hear you.
Yeah, so is it correct that when the Schwarzschild radius goes to 0, that is not equivalent to having a point particle? Is that correct? A point
Well,
for
Well,
either
it's-
generating the Coulomb
the
or
idea is that when the Schwarzschild radius goes to 0, you recover the Coulomb problem. Because this is just done within the context of the Schwarzschild geometry. And so we're no longer doing a self-consistent calculation, but instead we have some point source that produced that Schwarzschild geometry, and we're letting the Schwarzschild radius go to 0 and recovering an ordinary Coulomb Newtonian problem.
Oh, yeah. Okay, good. Thank you.
Yeah. This plot is a plot of that table that I showed earlier. These are those energies. This was the minus 1.63 approximately here for the non-relativistic case. And then as zeta s is increased, you get this significant change for the ground state where the relativistic one is pulled in to smaller radii and the energy goes lower. The others are not affected so much. And the plot, it's really hard to see if there's much of a change. If you look at the table, it does show some change. There is a recently a paper that came out. It was in the archive, but I think it's actually been published now very recently at PhysRevD, where they were looking at the Schrodinger-Newton problem and calculating what are called post-Newtonian corrections, which is basically looking at GR as an approximation, as a in the limit that you recover only leading corrections to the Newtonian description of gravity, and then introduce those corrections to the Schrodinger-Newton problem and recalculate what the energies are. So they were doing it from that perspective rather than what we did, which is the full relativistic calculation. And here are the amplitudes for each of the number of radial nodes. This is the 0 node case, this is the ground state, and plotting for several different zeta s values. You cannot see the non-relativistic value, the non-relativistic function, because it's sitting right behind this 0.01 case. They're basically on top of each other. So what you do see is that as zeta s goes up, we have more and more relativistic effects. The peak is made more narrow and it's pulled to smaller radii. So you're getting stronger attraction, smaller compression as you include these, making it more relativistic. Similar effects happening, even though you don't see much of an effect within the eigenvalues themselves, the amplitudes, you do see a significant shift in this second peak. This one, not so much. And I suppose the fact that there's very little change here between different zeta s values, that's why the eigenvalue is not changing very much, because it's in this region that you'd expect the dominant contribution to the energies. But there is a significant effect on the amplitude here at the second peak where it's pulled in. And this obviously is the one node solution. Here is the two node solution. And again, you see in this third peak, a significant change as you change the zeta S values and make relativistic effects greater, pulling it in. But we do recover in the other limit as zeta S is getting smaller, we do recover the non-relativistic results as expected from that claim that by considering a Schwarzschild geometry, we can identify zeta S as the key parameter for deciding whether or not the system is relativistic. So the next thing I wanted to talk about in a couple slides on what could be done next. And the one thing that we thought about is you consider, instead of spherical symmetry, cylindrical symmetry. Now, in the context of the Klein-Gordon equation and GR, that would be a significant increase in difficulty. Presumably, there are things that one could find, and so you didn't have to do it all yourself. You'd find things that are let you solve the general relativistic problem within that symmetry. Zach could probably tell us all about that. But if you look at it from a non-relativistic standpoint, it's relatively straightforward, because then what you're talking about is solving the Schrodinger equation in 2 dimensions in terms of a transverse radius rho and a z coordinate. And you have to find this potential by solving a Poisson equation for gravity, where the source comes from the absolute value squared of psi. And you can categorize these solutions because this V commutes with LZ. So LZ is still a good operator here, and you can search for simultaneous eigenstates of LZ and the Hamiltonian. And so we know right away that the phi dependence has to be the simple exponential factor. And when you take the absolute value squared of this, of course, the phase goes away. So the potential can be computed just in terms of rho and z. Now, in Harrison's thesis, he actually assumed that the wave function itself was independent of phi. And so he missed all these solutions that would be associated with higher LZ. And so what we're thinking about doing is going to situations where you do have a non-zero ML and calculate additional solutions out in that direction. There's been some recent work also looking at this cylindrical symmetry situation, although not so much from a bound state perspective. Now, just because we're working with cylindrical symmetry doesn't mean you need to use cylindrical coordinates. And in fact, if you use spherical coordinates, it's easier to see how to recover this spherical case as a limit, which is another thing that I didn't see happening in this thesis, where he showed that you can recover the spherical case as a special case of cylindrical symmetry. But I think we can do it more directly. If we look in terms of spherical coordinates, we can rewrite that Schrodinger equation in the usual way, where you have an L squared term, so you have the usual centripetal term, and you have also an equation for the gravitational potential in terms of spherical coordinates, and we've still got LZ, and we can now expand both functions in terms of spherical harmonics and truncate that expansion as the approximation to be made here, and create coupled equations between the coefficients of these expansions. And that would give us coupled systems of ordinary differential equations instead of solving two-dimensional PDEs, which you would on that previous slide. But either way, it has to be done self-consistently, because the solutions of one set of equations feeds into the structure of the other system of equations. The one integral that shows up in doing that representation is this integral over 3 spherical harmonics. But that's known. You can look it up in Sakurai. And the 3rd edition is this particular equation, gives it in terms of Clebsch-Gordan coefficient, so it's something that's known and computable. Those ordinary differential equations are easily approximated with a finite difference approximation. You have very simple boundary conditions on the functions that appear there. And so you can solve this all iteratively as a pair of linear systems. And the matrix representation for the Schrödinger equation is, you can think in terms of blocks between different angular momenta that would appear in the calculation. And if you want to recover that spherically symmetric case, it's very simple. You just make the ansatz that you don't have any higher spherical harmonics, and you immediately reduce down to single ODEs for each of the systems, and you recover what we were solving already. So from this perspective, it's automatic that you recover the spherically symmetric solution for that non-relativistic case. So just to summarize what we've said here is that we can incorporate general relativity as a description of gravity into the Klein-Gordon equation, look at it from that perspective, or we can look at Newtonian gravity, incorporate that into the Schrödinger equation. And in both cases, you have a nonlinear equation or coupled set of equations that have to be solved simultaneously, either way you want to look at it. And we get soliton solutions to those that determine self-consistently the distribution of the particle as well as the gravitational potential in which it lives. And these two approaches agree in the appropriate limits. We can take the non-relativistic limit of the relativistic case and recover the Schrödinger part. And it does seem that we can extend beyond spherical symmetry and look, do some work beyond what's already been done in cylindrical symmetry. Thank you for listening.
What's the motivation for going to cylindrical symmetry? Is there a particular situation in mind that would lend itself to helping understand?
Well, it's simply an extension. And one way to look at it is it's an extension of a calculation that's been done. And the question is, what can you find in the way of stable solitons that don't have the spherical symmetry?
Okay.
But it's also that most black holes in the universe are spinning. You don't find black holes that don't spin. You know, the universe has this pull in your arms, you spin, so there are cylindrical symmetry seems like the more natural symmetry for the universe.
Thank you. Yeah.
Yeah.
Okay. Makes sense.
There was a hand up online, Dylan. Sure.
Yeah, anybody online? Yeah.
Oh, Zach. I don't know what happened to Dylan. Dylan had his hand up first, but he doesn't have it up anymore. Okay. So we got Zach.
Yeah, sure. Hey, John. Very nice talk. Yeah, this is a neat strategy. I like this. It's really cute. Very neat. So going back to one of your earliest slides, where you talk about point particles technically are black holes. I am curious. The minimum radius for an electron, right? This is something that has been experimentally probed. Like, what is the radius of an electron? And as far as we're aware, right, it's a point particle. In fact, has the minimum radius of an electron been?
So
Yeah,
the electron can't really be a point particle because QED gives it structure.
Right. So
Yeah.
I guess my question is, what is the currently minimum bound or maximum bound on the radius? Is that smaller or larger than its inferred Schwarzschild radius?
The last number I saw was about 10 to minus 18 centimeters for upper limit on what you call the size of the electron.
Okay.
And that's significantly larger than the Schwarzschild radius for that kind of amount.
Right.
So my remark about a point particle being a black hole applies to literally a classical point particle.
Yes,
So
of course.
write down the Schrödinger equation for a point particle. You've already made an assumption that's incorrect in some sense. And so conceptually, one would want to think in terms of the particle being closed out somewhat. Now, as soon as you have a particle that is involved in an interacting field theory, like an electron interacts with photons, you no longer have a point particle in any real sense because the electrons producing and absorbing photons all the time, so it has structure.
Right,
It has
right.
some. Experimentally, it may not have pushed to it yet, but fundamentally it's just there. And I would imagine it's larger than the structural radius.
Sure,
but
sure.
probably was. That answer your question?
Yes, thank you, John. I appreciate it. And again, nice talk.
Okay, next, Rupert, you raise your hand.
Yeah,
have a question?
okay, can you hear me? So, John, as you know, for the ordinary Coulomb or ordinary hydrogen problem, there exists also a relativistic approach, and that's a Peter-Salpeter equation. Now, when in your approach here, you use a static metric, does then your problem, your solution merge or move towards solutions that you would get from the Peter-Salpeter equation?
Well, you're asking, can we solve the Peter-Salpeter equation in this sort of way to couple it to a gravity and solve it just a way?
Yeah, when you have static.
No, have not thought about that at all.
Mhm.
And as soon as the situation isn't static, then you have to ask Zach to calculate all the symmetric force, I suppose. Because that's not a big problem.
Mhm.
Have not thought about it much.
Okay, thank you.
Who is? Oh, Matt. Yeah. Go ahead, Matt.
I just wanted to ask, like, so you showed values of what the wave function looks like up to zeta s equals 1, and they still look fine in the sense of they're not diverging or doing anything weird. Would zeta s greater than 1 still correspond to a physical system?
Well, remember the zeta s is the ratio between the Schwarzschild radius that would be attributed to the mass if the mass were a point.
Right.
But it's not, it's spread out on scales associated with the gravitational border radius. And so this is a ratio between the two. And the mass distribution, so the question would be then, how much mass inside the what's called the Schwarzschild radius for this mass? And we didn't actually calculate that. But since everything was well defined in the calculation, I assume that that's not true. I would expect to see a collapse of things somehow.
Right. I was kind of wondering, if you keep cranking up zeta s, do you eventually hit that point? And I was wondering where it might
I
happen.
would assume so. We just didn't, as I said earlier, we just didn't, we weren't looking for trouble, but in doing the numerical calculation. And so we were focusing on the limit where we could make a correspondence with a non-relativistic case. But yes, I think if you push zeta up high enough, then something should happen where you can see some collapse. That'd be interesting calculations to do, I suppose. Another interesting calculation that your question made me think of, and I suppose I should have thought of it already, and that is one could calculate how much mass is inside the effective Schwarzschild radius and see whether or not there's some inconsistency there, or consistency as to whether or not it should be collapsing. And it didn't. So it would be an interesting calculation. Yes. Thank you.
Okay, thanks. Interesting.
Thank you. Any questions from students? Okay, then I'm shooting probably the last question. So based on your method, a calculation, I'm just curious whether that can calculate photons or not, or
I'm not sure what you mean by calculate photons.
the photon, the quantum effect, or those
You mean
gravitation
you want to look at transitions?
transitions, yeah.
Oh, well, I suppose one could associate some sort of transition between these different levels.
Mhm.
And if it's a charged particle, then you could imagine the transition associated with a photon. But I don't know if it's consistent to then not take into account QED in other ways as well, if you're going to formulate the problem. So it might not be really a consistent way of describing things without doing a much
And
lower.
also the photon don't have a mass, then probably another problem.
Well, yeah, but they have an energy density.
Yeah, certainly, they
So,
have energy.
yeah, right,
density about it,
yeah.
Right.
Yeah.
Okay, let's give a big. Okay, good.